Hello and welcome to Honors Function. In this third and last lecture on linear equations, we will be exploring the relation between two lines. Geometrically, there are three different cases about the relation between two lines. Okay, so let's quickly check graphically what's going on. You could have the two lines first of all to be the same, written in different equation, but actually they are describing the same kind of line. Okay, that's the first possibility. Second possibility, the two lines could be strictly parallel. That means they would never intersect. And finally, the third possibility, the two lines could intercept. Okay, and in this case there is actually an interesting subcase of this one is when the two lines would intersect at a right angle. Okay, so this is a different case. They intersect at a right angle. It's not a different case. It's a particular case of the last one right here. Okay, so let's first start this lecture by looking at this case right here, and this one. Okay, so first the line do not intersect and they are strictly parallel, and second the line intersect and they are perpendicular. So first let's take two lines, L1 and L2. These are lines, therefore they are sets of, this is a set of points and this is another set of points. There are sets of points. Okay, they are not numbers, nothing like that. In geometry we would write it like that, L1, and we would put a symbol for a line on top, but I don't want to use that here. Okay, and then a line has a slope, therefore I'm going to assume that its slope is M1. Now this is not a set of points, this is a real number. Okay, and L2 would have a slope of M2 right here, and that again is a real number. All right, so L1 is parallel to L2 if and only if it goes both ways. Okay, these are two conditional statements, reciprocal of each other. If and only if what? The slopes are the same. M1 is equal to L2, M2. And then L1 is perpendicular to L2 if and only if the product of the slope is equal to -1. So this is a result that I will not prove. It should have been done before. We don't need to prove it in this class. Okay, let's practice some examples. So in the first example, you have to find an equation. Now, I'm not specifying what kind of equation, right? So you're free to choose. You know, there are different forms for it. An equation of the line parallel to this line, and that goes through this point. So let me not graph exactly this line and this point, but basically this is what's going on right here, right? I'm giving you a line, this one right here. It's got a positive slope, so I'm going to make it go up right here. And I'm giving you a point. I hope the point is not on the line. So let me take the point, for example, right here. Again, I hope it is not on the line. If it is, then the line would be, the line I'm looking for would be this line itself, okay? What do I want? I want the equation of this line right here. There's only one line parallel to a given line going through a given point outside the line. This is actually a result from geometry. It's actually one of the main postulate in geometry. It's called the fifth postulate of Euclid. It's a very interesting one. It has a very long history in mathematics. Fascinating postulate. Anyway, how do we do that? Well, hey, let's get the slope of this line. So what's the slope of this line? -a over b, right? So it's written in standard form, so I'm using this equation right here. So -a, so -3 over b over -5, so it is 3/5. What's the slope of a parallel line? It's the same thing, it's 3/5, okay? So what's the equation of the line I'm looking for? I'm going to use a point slope form, y minus 5, right? That's y minus y1 equals 3/5 times x minus x1, x plus 3. That's it. This is an equation of a line that is parallel to the given line going through a given point. Okay, let's move on. I'm going to do the second example and I will let you tackle number 3. Okay, so in this case, what's going on? I want the same thing, except that this time I'm looking for a perpendicular line. So what's going on here? Again, I have a line, a given line, and I have a given point outside the line. And I'm looking for this line right here, the line that is perpendicular to the given line going through the given point. Now this in geometry is not a postulate. This is a result. You can prove that this line exists and is unique. I really loathe all geometric book that call this a postulate. I've seen it. It doesn't make any sense. You don't have to prove it if you don't want to, but don't call it a postulate when it ain't a postulate. All right, that was my rant. Let's move on. How do we do this one? Well, this is again pretty straightforward. Let's get the slope of this line. The slope of this line is negative a over b, so it's negative 2 over 5. Now, I want the slope of a perpendicular line, so the slope of the perpendicular line will be the opposite reciprocal of this slope right here. So it is 5/2, okay? First, you got to take the opposite, and then you got to take the reciprocal. All right, 5/2. Let's just write the equation. Y minus 1 equals 5/2 times x minus 2. Okay, 1 and 2 are coming from this point. I told you the point slope form is the most useful, the easiest to use, the most common. All right, please do number 3. Let's move on now to study the relation between two lines in more details. So we started the lesson by looking at all the various cases that two lines could interact with each other in the plane, okay? First, they could be the same line. Then they could be different but never intersect. That's strictly parallel. Or they could intersect, okay? So now we want to look at the algebra behind these various geometrical cases right here. So what we are given is two equation of a line. So for example, a1x plus b1y equals c1. I'm going to take standard form, it's easier, okay? And a2x plus b2y equals c2. Okay, I'm given two lines, line L1 and line L2, and I want to figure out where they intersect. In the first case, right here, they would intersect for any points on the line. So any points on the line L1 or any points on the line L2 would be a solution, okay, for this. In the second case, there wouldn't be any solution. And in the third case, there would be only one solution. There would be only one x and only one y. That would be the solution, okay? So how do we find out the first case? If you solve the first case, you would fall on something really trivial, like there are different ways to solve it, and I'm going to show you how. But at the end of the solution of the first case, you would find, for example, 5 equals 5, or negative 2 equals negative 2, or 0 equals 0. And in this case, you would say that any point on the line is a solution. In the second case, at the end of the solution of your second case, you would find, for example, 2 equals 1, or negative 5 equals 0, or 6 equals 1. And this, of course, makes no sense. There's no solution to the system. And in the third case, of course, you would find some valid solution, x equals a and y equals b. Okay, these are the three possibilities. So how do we solve a system of linear equation? Well, first, you could graph the line and solve them just by eyeballing where the solution is. This is what I'm doing in example number 4. And if you don't do it graphically, you have two possible ways to do it. You can do a linear combination or you can do a substitution. Let's go over the three methods right now. For the first method to work out, the graphical method, you really have to be very, very precise in the way you graph the lines, okay? So here are two equations of lines written in standard form. Let me graph them. Please don't change the form right here. Remember how to graph this kind of line. Just get 2 points. It's very simple. So I'm going to call that L1, and this one I'm going to call it L2. So let's get 2 points on L1. 3, multiple of 3 and multiple of 2, difference of 4. So how about 6 and 4? So I need a negative 4, so that's negative 6 plus 2 equals negative 4. All right, so I'm going to have the point negative 2 for x and negative 1 for y, right? 3 times negative 2 minus 2 times negative 1 is negative 4. Here's 1 point. I need another one. Well, let's take the other one. Let's take a 6 and a 10. 6 multiple of 3, 10 multiple of 2, and you can make a negative 4 out of that, right? It's 6 minus 10. So what's the point? Here it's going to be 2 and negative 2 times 5 is negative 10. All right, so let's plot these 2 points. Negative 2, negative 1, negative 2, negative 1, and 2, 5, 2, 5. Oh, I'm right outside right here. Okay, and now, as I said, you really have to be precise to graph that. So let's graph it here. Actually, I could have picked this point too, right? If y is 2 and x is 0, that's your y-intercept. And we even have the slope. The slope is 3 on the rise, 2 on the run, 3/2. Look at that. Let's graph this line. Here we go. Oops, that's really not... Okay, let's try to do a good job at graphing this. You really should use a ruler if you want to do the graphical method precisely. Okay? All right. Here's the first line. Second line. So for the second line, we have this equation. So there is an obvious point for the second line. It's x equals 7 and y equals 0. Okay? So 7, 0. Oops, I don't have it here. That's going to be tricky then. All right. I need to find another point right here. So I'll take x equals negative 3, right? Negative 3 plus 10, right? So I don't have this point. Too bad. I didn't make my graph big enough. I'm not sure it's going to be precise here. Negative 3 plus 10 is equal to 7. So x equals negative 3 and y equals 2. So let me take negative 3 and 2, negative 3 and 2. And you know what I'm going to do right here? I'm going to use my slope. It's going to be easier. And the slope is negative a over b, right? So m is negative 1 over 5. Okay, so let's do that. Negative 1 over 5. I'm going to do negative 1 over 5, okay? Mind you, I could also look at 1 over negative 5, all right? 1 over, here it means you drop 1 and right 5. Here it means up 1, left 5, okay? That's what it means. All right, so let's drop 1 and go right 5. 1, 2, 3, 4, 5. Check it out. 2, 1 should also be a solution, I'm pretty sure. All right, and here's my line. And so I'm gonna eyeball this. I really do not like this verb. I'm gonna eyeball this, and I'm gonna say the intersection seems to be, for the y I would say 0.5. It seems pretty accurate, 0.5. For the x, maybe I would say, I don't know, maybe 0.25, 0.3, 0.25, maybe 0.3. All right, I'll say 0.3, okay? So you see, you cannot do a very accurate job like that. All right, let's go over the second method. The second method is called a linear combination. It's also called an elimination method. Linear combination because I'm going to combine these two lines so that I will eliminate one of the two variable, okay? So in this case, it's pretty simple. The coefficient of x in the second line is 1. Let me eliminate the coefficient of x. So I will keep the first line as is, okay? I'm not changing the first line. And I'm going to multiply the second line by negative 3. I'm going to multiply both sides by negative 3. I like to add my lines, my equations. I don't like to subtract because I make mistakes when I subtract. So let me multiply the second equation by negative 3, and I'm going to write it right under. So it's negative 3x, negative 3 times 5 minus 15y equals negative 3 times 7, negative 21, okay? And now what? Now I will add side by side. I'm allowed to add two sides of an inequality. That will just cancel. Negative 2 and negative 15, that's negative 17y. Negative 4 plus negative 21 is negative 25. And so we have y equals 25 divided by 17. Okay? Now, at this point, very often, teachers will say to substitute this expression of y, this value of y, in one of the two equations. But that is messy, okay, because the denominator is 17. Moreover, if you've made a mistake in this one, the second one is going to be wrong no matter what. So I strongly suggest that you don't do that. Don't do that. Do another linear combination, and this time you eliminate y. It's going to be safer. Even if the first one is wrong, your second one may be correct. So now I want to eliminate these two coefficients. I'm going to multiply the first equation by 5. 15x minus 10y equals negative 20. And I'm going to multiply the second equation by 2. 2x plus 10y equals 14. So what do we have when we add side by side? 17x, of course, no y, equals negative 6. X equals negative 6 over 17. What is your solution for the system? It is negative 6 over 17, 25 over 17. Let's compare this value to our graphical solution. Negative 6 over 17 is actually about negative 0.35, and 25 over 17 is about 1.47. So I think it's kudos on this one, and we were a little bit off on this one, right? Let me see. I was. See, I like to say we when I make a mistake like that. Oh, it's not bad. I said 0.3. I started by saying 0.25, but then I realized it's a little bit on the other side. 0.3. Oh, heck. Kudos for both. All right. Okay. The last method to solve a system, by the way, I really like this one. Okay. This is my favorite method, linear combination. The last method is called a substitution. So I think you've all done it. I'm gonna let you do, actually I've made a mistake, I realized that. I think I wanted to illustrate substitution right here, and I asked for linear combination. So please try a substitution on this one, okay? Don't do a linear combination, try a substitution on this one. This method works nicely sometimes. Okay, you gotta be smart. You gotta take one of the two equations and solve for one of the two variables. Actually, you know what? I'm gonna let you do this one, and I'm going to do this this one right here. Please don't take the first equation and solve for x. That would be ridiculous. Okay, because you would have x equals. So if you solve for x, you find 2/3 of y minus 4/3. And then what do you do with that? You take this expression and you plug in the second equation. Now this is ugly. This is not smart. Really, if you want to do a substitution right here, it's a no-brainer. You got to solve for x right there, right? X equals negative 5y plus 7. Now you're going to be taking this one right here, this expression, and plug it in this equation right there. So what do you find? 3 times negative 5y plus 7 equals negative 4. Oh, sorry. I forgot my y's there. Minus 2y's equals negative 4. So you have negative 15y plus 21 minus 2y equals negative 4. So how many y's? Negative 17y's. Negative 17y's equals negative 25. Y equals negative 25 over, sorry, positive 25 over 17. And now what? Now you take this and you plug it in there, in the equation that was solved for x. And you see, this is not very fun because you have a fraction. Negative 5 times 25 over 17 plus 7. Oh my gosh, this is not very pretty. 5 times 25, 125. Negative 125 over 17. Now, common denominator here is 17. So 7 times 17, that's 70 and 49, right? 7 times 10, 7 times 7. 70 and 49 is 119. So it's 119 over 17. And negative 125 plus 119 is negative 6 over 17. That's exactly what we had. Do not forget to write the solution of the system. Negative 6 over 17, 25 over 17. Okay, so this is a brief recall of the 3 methods to solve a system of linear equation. Please do the last one. Which is actually example 6 right here for you, using a substitution method. Okay, thank you for watching.